Hi, welcome back, guys. After a short break, we were just talking about the molecular structures as far as covalent bonding takes place between atoms of non-metallic elements. Right. The next part of covalent bonding that we shall look at is what we refer to as covalent network structures. These are network structures, as you may recall even from your biology that you did in the first term, your life sciences, we spoke about macromolecules. Right. Sometimes we refer to these covalent network structures as macromolecules. Right. They're called macromolecules. Okay, right. Having said that, they consist of millions. Now, in terms of quantity, remember we said these are macro. Macro means large scale, big, huge, comparatively in size, if you want to think of it that way. Right. So they consist of millions. Still, it's non-metals because it has to do with covalent, which has to do with the sharing of electrons at the highest energy level. Right. So the atoms are bonded together by covalent bonds. So it means they overlap each other, these high energy orbitals, to form bonds. Right. It's a large and repetitive crystal. Sometimes we refer to them as the crystal structures or the network crystal structures, which consist of atoms that are bound together by strong covalent forces. So still, now, if you contrast this or compare it to the molecular structures that we discussed before the break, we agreed that as far as these molecular structures are concerned, it has to do with the bonding, which is the sharing. Now, remember, these can happen between atoms of the same kind, which we refer to as molecules of an element, or rather molecules of compounds. Now, let's go further and check. It says the structure have high strength. These I would want to think of them as the physical properties. Now, because they are giant structures or macromolecules, they are stronger compared to these, which are most often liquids, in gases, except for sugar, of course, it's solid at room temperatures. Now, they've got high boiling points, high density, which we discussed as the physical properties in the first term when you looked at physical properties of materials. So I'd want to think of these macromolecules as giant structures which are comparatively have got higher strength, boiling point, melting point. You'd even think of density as one physical property. That's to touch base with that. Now, let's look at the typical examples of these macromolecules. Right. Now, if you check, here we've got a structure. This represents diamond. Right. Diamond is a hard material. Remember, we said it's also used for cutting tools. Because of its high strength relatively. So it's a very much useful everyday application. Now, because we said that they've got comparatively stronger, they've got higher strength, melting and boiling points, which are the physical properties. So this is it's made up of carbon. Now, these are atoms of the same kind. These are carbon atoms, which are chemically joined together, covalent. But they form a huge structure which we refer to as a macromolecule. Now, you'd want to think of carbon as a diamond, rather as an allotrope. If we talk about allotropes, I think that's another term which is very key. We're talking about substances which are made of the same type of element, but they differ in structure from one to the other. The other allotrope of carbon, if you can think of it, is this one that we have, which sometimes we refer to as graphite, the gray substance which is used even in the pencil lead. So these it's a different structure to carbon because of the type of bonding is the same. However, the conditions under which these are formed, they differ one from the other. So these are what we call the giant structures or lattice structures. So carbon forms allotropes such as diamond as well as graphite. So this is a giant structure or lattice structure of a substance. So we call these network structures, covalent network structures. Covalent, why? Because of that which is the bonding. That's covalent bonding between the atoms of the same kind. Now, so this is a giant network structure of an element instead of a compound, because these are atoms of the same kind, right? So this is covalent bonding. very key also to recognize that fact, right? And then examples of other network structures include diamond and graphite, as shown in the example that, and also silicon 4 oxide or silicon dioxide, which is also a giant structure, and some of boron compounds. Some of them, definitely not all of them, as you'd realize as we go further, right? Okay, so now we've spoke about the two different types of covalent structures, the molecular, which are comparatively smaller in size, and also we've spoke about the network structures, which are giant, which we refer to as macromolecules. Macro meaning big comparatively in terms of unit size. Right. Let's move along. Right. Now, the other key concept, which is also key because we're still talking about bonding, metallic substances, we want to be very careful as far as metallic is concerned, because this also has to do with between atoms of metals. So as we talk about metallic substances and metallic bonding, it has nothing to do with compounds, because these are atoms of the same kind. So the metallic bonding will particularly take place between atoms of the same kind, between atoms of the same kind, right? Of the same kind. So now this is particularly very prevalent with the transition metals, the block of metals in the center of the periodic table, which is very key. As I've said, we shall constantly refer to the periodic table because it kind of guides us as to what exactly is taking place. Now, in terms of classification, when we talk metallic bonding, it has to do with in most cases, it has to do with the transition metals. You take gold, silver, zinc, iron. These are the most common examples of metals in which metallic bonding takes place, and we shall refer to those as metallic substances because they are elements instead of what? Of compounds, due to the fact that it has to do with the same kind of atoms being bonded together. Now, so the atomic nuclei, is always positive due to the occurrence of the protons in the nucleus of the atom. Now, the electrons in the underlying shells are surrounding the positive metal ion, which we have said is because of the protons, and these are tightly packed together and organized as crystal structure, and the outermost orbitals overlap each other. Now, the overlapping each other is what brings about the bonding aspect of it as far as metallic bonding is concerned. That's the valence, which we refer to electrons at the highest energy level or high energy electrons. So valency are those high energy electrons, in terms of the orbitals. So these are high energy electrons, which are delocalized. Delocalized, it means, I think in simple language, it would refer to electrons being displaced. They're not going to be confined around that nuclei of the atom. It means the adjacent nuclei between the adjacent nuclei, these delocalized electrons can actually move between them, creating that sense of element of that aspect of bonding, which we refer to as the metallic bonding, right? Now the smallest particle or the unit that makes up a metallic crystal, right, is what we call the positive metal ion core. So, or alternatively, we shall refer to it as an ion, right? The examples, like I said, copper, iron, zinc, and silver are your typical transition metals. These are the most common examples of substances that have got what we refer to as metallic bonding, right? Very, very important. Now, so metallic bonding would only take place between atoms of the same kind, particularly of the metal. I think after all has been said and done, that's what one needs to take home with in terms of metallic bonding. So the three types of bonding that we've looked at is the covalent. It's the covalent, which is divided into two, which is molecular, which forms molecular structures and network structures. Now, we've also looked at the metallic bonding. Right, let's move along and look at the the next concept, which has to do with the types of formula. Right. In terms of ionic bonding, maybe before we look at formula, in terms of ionic bonding forms between metals and non-metallic atoms. In other words, ionic bonding will take place between two atoms of different kinds, in the sense that compounds would rather be formed instead of elements. Right. So as far as formula is concerned, we use there's what we refer to as molecular formula. I'm going to use water as an example. H2O is the molecular formula that would use to represent the substance water. Right. Now, this type of formula is the actual number. In other words, it says in a unit of, or in a molecule of water, there are 2 atoms of hydrogen bonded to one oxygen atom per molecule. Now, then it means if we have a substance like water, would have these chemically joined together, then they will also have their own forces between other. But now our focus for now is rather the fact that the actual number of atoms of each element in this compound is 2 for hydrogen and 1 for oxygen. So the individual atoms, in this case, we've got 1 atom for hydrogen, right? Which is is 2 atoms for hydrogen, right? And 1 atom for oxygen. So this would be our typical what you call a molecular formula. This is the type of formula that we use to identify the substance. And then we talk about the empirical formula. So the empirical formula shows the simplest whole number ratio. In other words, for water, it's still we can't further simplify the ratio 2:1 in terms of hydrogen to oxygen. Let's look at another substance with the same composition, which is also a pure substance and a compound. Let's take hydrogen peroxide. Hydrogen peroxide is H2O2. Right. Now, if you think of it, it contains 2 atoms of hydrogen, 2 atoms of oxygen per molecule, which is the actual number, which is the molecular formula, okay, of this substance. Right. Now, and then if we want to go to the empirical formula, it means we can simplify this into a simplest ratio we can get. In other words, it would be 1:1. In other words, 1:1. 1:1, because for every 2 hydrogen, we've got 2 oxygen. So in other words, the empirical formula would be HO, which means 1:1. Now, in this case, the molecular formula of hydrogen peroxide is different from the empirical formula. Whereas in water, the molecular formula is H2O. It means if we can't simplify this further, it means the same molecular formula will also be empirical formula for water. So we need to also be careful. And then in this case, this will be a different empirical formula to the molecular formula of the same substances. So the smallest repeating unit in this case is HO, right? Okay, right. Now, having said that, I think it's very important for us to also realize that these types of formulae, they vary. And maybe in some of the schools, we have the privilege of having the models that we use to present. We also have another type of formula, which is referred to as the structural formula. We can use the ball and sticks model, to play around and construct different models of substances, just to show how atoms, whether of the same or different elements, join together to form molecules. So in terms of structural formula, what would be key, I think, would be showing the actual bonds and the actual atoms, how they join together to form a unit or a molecule of a particular substance. Right. For now, I think we've discussed quite a lot. I think we need to take a short break. Then after that, we shall look at the feedback, the activities that I'll give you time to attempt. And then after that, we could maybe do feedback and consolidate. Let's just go and take a short break, and we shall be back after the wrap-up. Thanks.